Okay, so we're going to have a look at video, guys, to try and help you with the first part of the organic chemistry topic in A2 chemistry. Okay, so this is to do with isomerism. It applies to, it will apply to a bit of the inorganic chemistry we'll do later, but at the minute we apply it just to the organic chemistry. So I'm going to run you through the part where they're doing class. For those of you who missed it in the first session, we'll do a few past paper questions, a few examples, just to make sure that we've covered sort of all bases. So the first part of this is I'm looking at, and I'll run through this pretty quickly. This is looking at a bit of revision from last year because there is a synoptic element to this isomerism, in that stuff that you did in the AS2 module will also come up on the A2-1 module and the A2-2 module. So don't think that your isomerism from year 13 is forgotten about. It's not. So the isomerism we looked at in year 13 was structural isomers, and those were molecules with the same molecular formula, different structural formula. On the next slide over, we'll look at some different examples of those. Okay, there's three different ones that you need to be aware of. And the other one that we looked at, and we looked at this a little bit last year, stereoisomers. This is the new one that we're going to look at this year, is a part of stereoisomers, but okay, you've already looked a little bit into stereoisomers, and that's isomers with a different spatial arrangement, but the same structural formula. So you have two different types of isomers there, two different definitions, one in the blue, one in the red. And of course, you'll have to know both. Okay, well, let's look at our structural isomers first. We have chain isomerism, we have positional isomerism, and we have functional group isomerism. So we have already done two of these. Okay, last year we looked at our chain isomers, we looked at our positional isomers. I might not have referred to them as chain and position, wasn't really required. I probably just called them structural. And this year within structural, we're going to look at our functional group isomers. So chain isomers is very simple. That's whenever you branch the chain. So if I was to say to you, could you give me a chain isomer of what is normal butane there, N-butane? Okay, I would like to think that you would probably be able to come up with the one that's coming up on the screen now, which is of course methyl propane. All right, so we're just taking a carbon off the end and we're popping it into a carbon which is in the middle. Positional isomers, you may or may not recognize them, but you'll know them pretty well. Things, if I said to you positional isomers, so we're really just changing the functional group. On the board there I have 1 bromobutane. I would hope you'd be able to tell me you could have 2 bromobutane. If I said to you, give me a chain isomer of that, well, I would like to think that you would maybe go, okay, well, you can have, take your CH3 here off the end and maybe pop it into the middle to give you methyl 2-bromo, sorry, start that again, 2-bromo methyl propane. Okay, so that'll be a chain isomer of that one, all right? But your bromo is still on position number 2, so it's not a positional isomer. Okay, right, and then finally the one that we're going to look at this year a little bit more, although it's not particularly difficult, are what we call functional group isomers, which again fit the definition of structural isomers, where they're the same molecular formula but a different structural formula. Okay. But this time they have a different functional group altogether. So whereas in positional isomers we were just moving the functional group around, now we're actually changing the functional group. And there's this functional group that is actually on the AS spec, and you should hopefully recognize that as an aldehyde. Okay, and a functional group isomer of an aldehyde would be a very similar molecular ketone, but nonetheless different functional groups, same number of carbons, hydrogens, oxygen, but different functional groups. Okay, other functional groups that you'll do this year, which are isomers of each other, would be carboxylic acids and esters. Okay, both relatively easy to recognize because they both have 2 oxygens in them. Alright, and they're the two molecules in chemistry level that have 2 oxygens in them. So when you see or ask for a functional group isomer of something and you see 2 oxygens in the formula, well, they're probably talking about carboxylic acids and esters, but not definitely. Right, let's shift on then to stereoisomers. Okay, so stereoisomers, we have geometric. Now we did geometric last year, and hopefully you can remember we talked about cis and we talked about trans and we talked about E and we talked about Z. Okay, so the criteria, if you remember, for these type of isomers were, first of all, when you were looking for it, you had to look for a double bond. So that was number 1 criteria. Then you had to look for a different group, 2 different groups, sorry, on the left of the double bond and 2 different groups on the other side of the double bond. So in other words, we had to say here that A was not allowed to be the same as B, and D was not allowed to be the same as E, and we had to have a carbon-carbon double bond, and if we met all of those criteria, then we could have EZ isomers. And then we assign those isomers with priority. Okay, so we give it to the atomic number of the atom directly attached to the carbon in the double bond. So we give it 6 and 1 here. So there was my, what we call our high priority group there. And we would have done the same over here, 6 and 1. We'd have had my high priority group up there, therefore, and that was the Z isomer. So the Z isomer was the isomer, if you can remember back to AS level. The Z isomer is the isomer where we have the two groups on the same plane. So that's the criteria for our E and for Z, and if you maybe want to have a read over that again from AS level, that would probably be worth your while. You'll see in the past paper booklet there's a few of these EZ and structural come up again. Right, let's look at the new one then, which is optical isomerism. Okay, and this is the one that we're going to spend most of our time looking at and answering questions about. So it is still a type of stereoisomer, but this time you're looking for a different arrangement of the four groups around that central carbon, okay, in a molecule, okay, and you will get what we call non-superimposable mirror images. So let's go through that again. You have four groups around, okay, around a central carbon. So that therefore rules out anything around a carbon-carbon double bond having this optical isomerism. So any carbon in a carbon-carbon double bond can't have it, because remember, the max you can only have there would be, of course, 3 groups around it. Now, of course, any other carbon, singly bonded carbon like this one, could possibly have it. Now, this one, of course, doesn't, because there's no way it can have 4 different groups around it. If it's a CH3 group, it's going to have 3 hydrogens. Okay, so we're looking for things like this. Okay, where we have drawn out the structure of the molecule, and we've discovered that there's a carbon in it, and we have a CH3. Note it says up here 4 different groups, not 4 different atoms. Okay, we have a carbon, a CH3, sorry, a hydrogen there, an OH group, and a CN group. Okay, and that carbon in the middle then is what we call this is an optically active compound, and that is your carbon, which causes, that will come later actually to the specific name for that carbon. Alright, now this molecule then exists as non-superimposable mirror images. Now you might think that if I took that molecule on the left and I took that molecule on the right and I set one directly on top of the other, that they would fit directly on top of each other, but they won't. They are what we call non-superimposable mirror images. Okay, your hands are probably the best example. So if you look at your two hands, they look essentially identical. If you hold the left hand up to the right hand, okay, as if they're mirror images of each other, okay, they look pretty much identical and are mirror images. However, if you go to superimpose them on top of each other, you will not be able to get the right thumb or any part of the right hand to superimpose part of the middle finger on top of the left hand, okay, and vice versa. So they're non-superimposable mirror images. Okay, so these things are phenomenally similar. Okay, phenomenally. The only way that we can tell the difference between them is their ability to rotate plane of polarized light, and that's where they earn their name, optical isomers. And we'll have a look at rotation of plane polarized light later on. Okay, so that's where they get their name from, their optical phrase from. Okay, now we're going to bombard you now with some new terms. You need to go to your definitions and make sure that you learn these terms, read through the notes, and make sure you familiarize yourself with them. So the two optical isomers that we had on the previous page, or anywhere two optical isomers, are called enantiomers. Okay, so that is your first word. These are the names given to the individual isomers. We're going to look at some amino acids here. Okay, and I'm going to point out just a couple of mistakes that sometimes students make when they're drawing them. Okay, so that's the amino acid. That's the same one on the left and the right, and that's the mirror images of them. Okay, right. So you're being introduced here to drawing structures in 3D, in three dimensionals. Okay. Now obviously there are many hundreds of ways to draw anything. If I put my hand in front of me and I want to draw it three-dimensionally, there are many ways to draw that structure three-dimensionally depending on how it's rotated in front of my eyes when I draw it. My advice to you is to get one method, ideally the method that's on the screen now, and copy it. And all you need to do each time is find the carbon, which has the four different groups around it, and draw a flat line here, a flat line here, a dashed line here, and a wedge from thin to thick here. Okay, and you do exactly the same on the other side, okay, but you make it a mirror image, okay. So your dashed line again comes out towards this one, okay. Your wedge is slightly angled in this direction, and your flat lines are mirror images again, okay. So get yourself one method, stick to it, and draw all of your optically active compounds through that three-dimensional orientation, which I have on the screen at the minute, and that will serve you well for A level. Okay, so we're going to come in with some, I just want to show you here just where people sometimes would lose marks and drop marks in an exam. So here, okay, where I have this COOH up here, sometimes people would be a bit sloppy basically, and they just write an H there and an OOC there, something like that. Okay, that will cost you marks. This carbon, which is what we have shown on the screen, is the carbon that's attached to the carbon in the middle, and that must be drawn in that way. Now, it would be fine actually to go like HCOOH like that. I don't think they'd take marks off you, but if you showed the H being attached, if you're sloppy and you did that, then you would lose marks. The same would be true down here, where some people would write NH2 like that with the 2 bonded to that carbon, or the hydrogen bonded to that carbon. That's incorrect. It's the nitrogen that's bonded. So please, especially for A2 level, where they're going to be a bit more stringent in their marking, please bear that in mind. Okay, so we've had some new terms here. We've had optical isomer, we have enantiomer. All right, we're going to give you another one. So that carbon that is in the middle, that is the four different groups around it, is called the chiral carbon. Okay, now that is a word that you need to be aware of. Okay, so a chiral carbon is the one, and they'll often ask you in a question to label the chiral carbon. That's what the chiral carbon is, and very often they'll say, okay, so draw your three-dimensional structure and put an asterisk beside the chiral carbon, and that's it. It's also called an asymmetric carbon, and those are two phrases that you would need to make sure that you're familiar with, because they'll be used frequently in exams. Okay, so that's what it is. Okay, now these things are absolutely identical in every single way, apart from they rotate plane polarized light in opposite directions. Now, you won't need to be able to work out in which direction they rotate that plane polarized light in. Okay, the second thing that is different between them is their biological activity. And this is where it becomes really very important that chemists and biochemists and pharmacologists understand optical isomerism, because if you're producing a drug to be manufactured and to be used in plants or animals or humans, if one of those drugs is optically inactive, well then it's essentially no use, despite the fact that the other drug, the other enantiomer, okay, may actually cure the disease or treat the illness. So that one there may be treating it, that one there may be actually ineffective. Now the problem with that is when you make this stuff in a lab, when you make it in a factory, okay, you always make it in a 50-50 mixture. It's really very, very difficult to make this actual enantiomer that you desire that actually treats the illness. So you have two choices. Your first choice is you give the entire drug to the patient, and there's an ethical issue there, because you're giving a drug to a patient who's probably already got compromised liver, kidney, okay, etc., just generally feeling unwell, and you're giving them 50% of a drug which their liver, their kidney, their small intestines, their stomachs all have to metabolize and get rid of, okay, but it actually does them no good. But the problem is, if I go to separate these two drugs out, because they are so similar, it takes the price of that drug and absolutely sends it sky high. And drugs are already expensive the NHS, or not the NHS, but just from drug companies, full stop, sorry. Okay, so that's a bit of a problem. Now, where you would definitely have to separate them out is if the other one, instead of being biologically inactive or just doing nothing, sometimes the other isomer actually, or the other enantiomer, can actually be harmful. Okay, so you may have one of the enantiomers, despite the fact that these things are so similar, you might have one that's able to do and cure the illness, and you might have the other one then, which in actual fact does damage to cells and biological damage to the body. So that is when you have a real problem and you've got to get them separated out. Okay, now, as I said earlier, the problem here is when you make these in a lab, you make them in a 50-50 mixture, and that's really, really hard to avoid. And that 50-50 mixture is called a racemate. Okay, you can see that word down at the bottom, or a racemic mixture. So we've given you three new terms on this slide: enantiomers, chiral carbon, and down here the racemic mixture, or the racemate. Now, if we go up to these two amino acids here, they obviously are optically active. So therefore, because they're optically active and they've got a carbon with 4 different groups around it, they will rotate plane polarized light. But if I take this mixture when they come straight out of the lab, they will have no effect on plane polarized light at all. And you might say, well, how can that be? How can they have chiral carbons? How can they have optical isomers but not affect plane polarized light? Well, I said earlier that they rotate plane polarized light in opposite directions. That is the only thing that separates them. So if I have a 50-50 mixture and I pass plane polarized light through them, they will rotate it in equal but opposite amounts, and therefore the plane polarized light passes straight through. So you get this point where you have optical isomers in a mixture, but the mixture itself is not optically active because the isomers are in a 50-50 mixture, or a racemate, or a racemic mixture. So it's an optically inactive mixture made of optically active molecules. Hope that makes sense. Okay, and the way in which we measure this rotation is through a thing called a polarimeter. And a polarimeter, very simply, is where we take it's basically a long tube, okay, where we pass into it some light, which passes through a Polaroid filter, which filters out all the light apart from light of one wavelength. So we've got plane of polarized light that passes through the isomers and it is rotated. Okay, so this isomer here of butanediol, it's what we call the R isomer. Don't worry about that. It's just one of the enantiomers, and then it passes also through at the same time through the S isomer. That's the other enantiomer, and that rotates it oppositely. So they're both have the ability to rotate the plane of polarized light, but because they're in equal quantities in the mixture, it turns out that the plane polarized light from the start of the polarimeter to the end is unaffected. Okay, so you have two optically active compounds in here. If you look, the chiral carbon is where I'm circling now. Okay, but you have a mixture which is optically inactive. Okay, so the one that rotates it clockwise is called dextrorotatory, or the D isomer. The one that rotates it anti-clockwise is levorotatory, or the L isomer. Now you don't have to know that for A level. You don't need to know the difference between D isomers and L isomers, so don't worry about that. Okay. Right, so what I'm going to do now, guys, is I'm going to cut to I've just got a few diagrams here which I want to take us through. Okay, few pictures, so these should pop up now, up a little bit. Alright, so this is just really referring back to what I sort of spoke about earlier there, where you will lose